Mars is hiding something beneath its rust-colored surface. Recent discoveries show ancient sand dunes soaked by underground water billions of years ago, leaving behind minerals capable of preserving signs of life. What scientists are finding challenges everything we thought we knew about where to look for life beyond Earth. The surface of Mars appears lifeless. Temperatures plunge to -80 degrees Celsius. Radiation bombards the ground with enough force to sterilize any exposed organism. Toxic chemicals called perchlorates saturate the soil, creating conditions that would kill most known microbes within hours. Yet beneath this hostile exterior, Mars may be concealing environments where life could persist, protected from the brutal conditions above. In 2001, the Mars Odyssey spacecraft revealed something unexpected. Large areas of subsurface water ice exist just below the Martian surface, far more extensive than anyone anticipated. The Mars Subsurface Water Ice Mapping Project has since mapped these deposits using radar detection, thermal infrared imaging, and neutron spectroscopy. Their findings identify specific regions, particularly Deuteronolis mensae and Arcadia Planitia in the northern mid-latitudes, where ice lies within reach of future drilling missions. This ice tells a story. Mars wasn't always the frozen desert we see today. Billions of years ago, the planet supported lakes, rivers, and possibly even oceans. Water flowed across the surface, carving valleys and depositing sediments. Then something changed. The atmosphere thinned. Temperatures dropped. Surface water vanished. But the story didn't end there. Even after Mars lost its surface water, something continued happening underground. Recent analysis of ancient sand dunes in Gale crater reveals they were saturated by groundwater long after the lakes disappeared. Water from nearby mountains seeped through tiny fractures in the rock, moving slowly through the subsurface. These dunes hardened into rock over billions of years, preserving minerals formed by that underground water flow. The minerals are crucial because they can trap and preserve organic material, the chemical signatures of life. This discovery fundamentally reshapes the timeline of Martian habitability. Scientists once believed Mars became inhospitable shortly after its surface dried up, perhaps 3.5 billion years ago. The evidence from Gale crater suggests otherwise. Protected environments beneath the surface could have remained habitable for hundreds of millions of years longer, maybe even into relatively recent geological time. The Chinese Zhurong rover provided another piece of the puzzle in 2024. Its ground-penetrating radar identified subsurface structures in Utopia Planitia that look remarkably like ancient coastal deposits on Earth. The radar revealed dipping layers inclined between 6 and 20 degrees, extending to depths of 10 to 35 meters along a 1.3-kilometer traverse. These structures match the geological signatures of shorelines, places where water once met land. What makes this finding extraordinary is its implication. Mars didn't just have scattered lakes. It may have supported an ancient ocean, complete with coastlines, tides, and a water cycle involving precipitation, surface flow, and subsurface infiltration. The ocean disappeared billions of years ago, but its legacy remains frozen in the geological record beneath the surface. Ice on Mars isn't just frozen water. It's a potential time capsule. The 2008 Phoenix mission was the first to physically dig down and photograph subsurface ice in Mars's equivalent of the Arctic Circle. That ice could preserve organic molecules and potentially even dormant microorganisms for billions of years. The permafrost environment acts as a natural preservation system, maintaining temperatures cold enough to prevent chemical degradation while shielding contents from the radiation that sterilizes the surface. NASA research has demonstrated that ancient microorganisms can survive for extraordinarily long periods when frozen in ice. On Earth, Scientists have revived bacteria from permafrost that remained frozen for hundreds of thousands of years. Some extremophiles enter a state of dormancy so profound they require almost no metabolic activity. Their cellular machinery essentially pauses, waiting for conditions to improve. If similar organisms existed on ancient Mars and became trapped in subsurface ice, they might still be there, suspended in geological time. But finding them requires going deeper than Phoenix could dig. Most of Mars's subsurface ice lies beyond the reach of simple scoops. The SWIN project produces ice consistency maps across different depth ranges, 0 to 1 meter, 1 to 5 meters, and deeper than 5 meters. Each depth range presents unique challenges for access and exploration. The subsurface isn't just about ice. It's about liquid water, the essential ingredient for life as we know it. In 2018, the Marseille's radar instrument aboard Europe's Mars Express orbiter detected something that sent shockwaves through the scientific community. Beneath Mars's south polar ice cap, approximately 1.5 kilometers below the surface, radar signals suggested the presence of liquid water. The signal was extremely bright, exactly what you'd expect from a reflective liquid surface. How could water remain liquid that deep beneath an ice cap on a planet where surface temperatures rarely rise above freezing? The answer lies in chemistry. Perchlorate salts, abundant on Mars, dramatically lower water's freezing point. A solution saturated with perchlorates can remain liquid at temperatures as low as -70 degrees Celsius. Such hypersaline brines could persist in pockets beneath the polar ice, protected from the cold vacuum above. Additional data revealed not just one potential lake, but 3 smaller bodies of water appeared in close proximity to the first detection, suggesting an interconnected system of subsurface reservoirs. These wouldn't be pristine mountain lakes. They'd be extremely salty, bitterly cold, and perhaps more similar to concentrated brine than anything we'd recognize as water. Yet extremophiles on Earth thrive in similarly harsh conditions. The finding remains controversial. A different radar system, SHARAD, detected only faint signals in the same area. Some scientists argue the bright reflections might come from something other than liquid water, perhaps mineral deposits or some quirk of the Martian geology we don't yet understand. The debate illustrates a fundamental challenge in planetary science, interpreting indirect evidence from millions of kilometers away without being able to physically sample what you're studying. Regardless of whether those specific detections represent actual lakes, the principle holds. Mars's subsurface offers conditions far more hospitable than its surface. Temperature swings are muted. Radiation is blocked. If liquid water exists anywhere on Mars today, it's almost certainly underground. The subsurface also contains environments we're only beginning to understand. Lava tubes, massive tunnels formed during ancient volcanic eruptions, honeycomb regions of Mars. When lava flows, the surface cools and hardens while molten rock continues flowing underneath. Eventually the eruption ends, the lava drains away, and a hollow tube remains. Some of these tubes on Mars are enormous, large enough to fit entire city blocks inside. Scientists studying lava tubes in places like Lanzarote in Spain's Canary Islands have found them teeming with microbial life. Bacteria colonize the walls. Calcium and sodium sulfates accumulate, chemical signatures that microbes were present for extended periods. These aren't random microbes. They're specialized extremophiles that thrive in darkness, extracting energy from chemical reactions rather than sunlight. Mars-orbiting spacecraft have identified numerous potential cave entrances, dark pits that might lead to underground tunnel systems. These shielded environments could be prime locations for finding preserved or even living organisms. The caves offer protection from radiation and temperature extremes. They're isolated from the harsh surface conditions. And if they contain ice or liquid water, they provide everything life needs to persist. What would Martian life look like? Almost certainly not little green men or even anything visible to the naked eye. If life exists on Mars, it's probably microscopic, similar to bacteria or archaea on Earth. It might be incredibly slow-growing, taking centuries to form colonies that would develop in days on Earth. It would be adapted to extreme cold, high salinity, and complete darkness. Understanding where to look requires understanding how life survives in Earth's most extreme environments. The Atacama Desert in Chile is one of the driest places on our planet, receiving less rainfall than even Antarctica. Yet microbial life persists there, sometimes meters below the surface. Scientists studying these organisms found they're distributed in patchy colonies related to moisture availability and geochemistry. Some depths had thriving communities. Other depths, just centimeters away, were completely sterile. The lesson is clear. Life on Mars, if it exists, won't be uniformly distributed. It will cluster in specific niches where conditions align: enough moisture, available chemical energy, protection from radiation, and temperatures that occasionally permit liquid water. Finding these niches requires understanding Mars's subsurface structure in detail we don't yet possess. That's where the next generation of exploration comes in. The technologies being developed to search beneath Mars's surface represent quantum leaps beyond anything we've deployed before. Ground-penetrating radar has fundamentally changed what we can see without digging. The technology works by sending radio waves into the ground and measuring how they bounce back. Different materials reflect these waves differently. Ice has a distinct signature. Rock has another. Liquid water, if it exists, produces a particularly strong reflection because of its high dielectric constant. The rovers currently exploring Mars carry sophisticated versions of this technology. Perseverance's RIMFAX instrument operates at frequencies between 150 and 1200 MHz, allowing it to image structures up to 10 meters below the surface with centimeter-scale resolution. China's Zhurong rover carries similar equipment, the roper system, which can penetrate even deeper in some terrain types. What they're finding is remarkable. In 2023, data from Zhurong revealed something unexpected in Utopia Planitia. The radar detected layers beneath the surface dipping at consistent angles between 6 and 20 degrees, extending for more than a kilometer. The pattern matched what geologists call a prograding shoreline, the kind of sedimentary structure that forms when a coastline gradually advances into a body of water. These weren't random reflections or instrumental artifacts. They were organized geological features with the exact characteristics you'd expect from an ancient ocean boundary. The layers extended 10 to 35 meters thick, undisturbed by the channels that would have cut through them if they'd been exposed on the surface for any significant time. The discovery wasn't just about finding evidence of water. It revealed that Mars once had a water cycle complex enough to create coastal environments, complete with sediment transport, deposition patterns, and the kind of gradual geological processes that take millions of years to complete. Why does this matter for finding life? Because shorelines on Earth are biological hotspots. They're transition zones where nutrients concentrate, where sunlight reaches shallow water, where chemical gradients create energy opportunities. If Mars had similar environments billions of years ago, and if those environments persisted long enough for life to establish itself, then the sediments beneath Utopia Planitia might contain preserved biosignatures. The radar can't detect life directly, but it can map the geological context, identifying layers where ancient microbes might have lived and died, leaving their chemical fingerprints behind. The challenge is interpretation. Radar data from millions of kilometers away requires careful analysis. You're looking at reflections, not direct images. multiple factors can create similar signals. That's why the Marcy's instrument on Mars Express sparked such heated debate when it detected bright reflections beneath the South Polar ice cap. The team interpreted those signals as liquid water, potentially a subsurface lake where extremely salty brine remained unfrozen despite temperatures well below 0 Celsius. Follow-up observations seemed to confirm the finding, even suggesting multiple smaller lakes nearby. But other radar systems looking at the same area saw different things. Zhurong, operating at different frequencies, detected much fainter signals. Some researchers proposed alternative explanations involving mineral deposits or layers of ice with unusual properties that could mimic the radar signature of liquid water. The debate continues because proving liquid water exists requires more than radar reflections. You need corroborating evidence from multiple instruments, theoretical models showing how such water could remain liquid, and ideally, direct sampling. What we can say with confidence is that Mars's subsurface contains structures we don't fully understand yet, and some of those structures have properties consistent with liquid water under specific conditions. That ambiguity isn't a failure of science. It's a recognition that we're operating at the edge of our current capabilities, interpreting indirect evidence from a world we've never touched. Autonomous exploration technologies are accelerating the pace of discovery dramatically. Traditional rover operations involve a time-consuming cycle. Scientists on Earth examine images from Mars, identify interesting targets, plan a sequence of movements and measurements, then transmit those commands. The rover executes them. New data comes back. The cycle repeats. This works, but it's slow. Light takes between 4 and 24 minutes to travel one way between Earth and Mars, depending on orbital positions. Round-trip communication delays can exceed 40 minutes. If a rover encounters unexpected terrain or needs to make quick decisions, it has to wait for human input. New systems change that equation. Autonomous navigation algorithms allow rovers to identify and prioritize targets without waiting for instructions. A rover can analyze a rock's composition using onboard instruments, determine whether it matches criteria programmed by scientists, and either move on or conduct detailed analysis based on that assessment. Field tests in Mars analog environments show these systems complete surveys up to 3 times faster than traditional methods while maintaining accuracy in identifying scientifically valuable targets. The implication for subsurface exploration is significant. Faster surveys mean more ground covered, more samples analyzed, more chances to stumble across the specific geological contexts where life might have persisted. But speed only helps if you're looking in the right places. That's where Earth's extreme environments become invaluable laboratories. The Atacama Desert in northern Chile receives less than 15 millimeters of rainfall annually in its driest regions. Some weather stations there have never recorded measurable precipitation. The soil is so dry that it resembles Martian regolith more than typical Earth dirt. NASA's Subsurface Life in Atacama project deployed an autonomous rover with a drill capable of reaching 800 millimeters below the surface. The mission wasn't just about testing hardware. It was about understanding where life exists in Mars-like conditions and why. The results revealed patterns that should inform Mars exploration strategies. Microbial communities weren't uniformly distributed. They clustered at specific depths where moisture availability, geochemistry, and salt concentrations aligned in narrow windows of habitability. Some samples contained thriving bacterial colonies. Others, collected just centimeters away, were completely sterile. The distribution correlated with subtle variations in sediment composition that affected how much water remained accessible to organisms. In the deepest samples, extreme salt concentrations created osmotic challenges so severe that even extremophiles couldn't survive. The lesson is clear. On Mars, life won't be everywhere, It'll be in precise niches where multiple conditions converge favorably. Finding those niches requires understanding not just where water exists, but where water interacts with the right minerals at the right temperatures for the right duration. Clay minerals on Mars tell part of that story. Clays form when water interacts with volcanic rock over extended periods, breaking down minerals and creating new compounds. The presence of specific clay types indicates not just that water was present, but how acidic or alkaline it was, how long it persisted, and what temperature range it maintained. Perseverance discovered clay-bearing rocks in Jezero crater that formed in conditions remarkably similar to environments where microbial life thrives on Earth. The rocks show evidence of prolonged water-rock interaction, not brief flooding but sustained aqueous environments that persisted long enough for complex geochemistry to develop. Sulfate minerals add another layer to the story. Sulfates typically form in more acidic conditions or through evaporation of mineral-rich water. Their presence suggests that Mars's ancient water chemistry varied significantly across different locations and time periods. Some environments were neutral and relatively benign. Others were harsh, acidic, potentially toxic. Both types might have supported life, just different kinds adapted to different challenges. On Earth, acidophilic bacteria thrive in environments that would kill most organisms, extracting energy from iron and sulfur compounds in solutions acidic enough to dissolve metal. The most intriguing recent discovery involves organic molecules preserved in rocks dated to 3.7 billion years ago. Curiosity's instruments detected long-chain hydrocarbons containing up to 12 carbon atoms. These molecules resemble fragments of fatty acids, essential components of cell membranes in terrestrial life. Can they form without biology? Yes. Meteorites contain organic compounds created through purely chemical processes in space. But the complexity and specific structure of the molecules Curiosity found make them compelling candidates for biosignatures, especially when found in geological contexts that also show evidence of liquid water and chemical energy sources. Perseverance's discovery of potential biosignatures in a rock called Chiava Falls represents perhaps the strongest evidence yet. The sample shows concentric rings of different minerals, vivianite surrounding cores enriched in gragite. That pattern matches electron transfer reactions observed in some Earth sediments where microbes extract energy from chemical gradients. The chemistry doesn't prove metabolism occurred, but it demonstrates that the right conditions existed, that energy was available in forms life could theoretically use, and that minerals capable of preserving biosignatures were present during the critical window when Mars might have been habitable. The rock is now stored in Perseverance's sample cache, waiting for a future mission to return it to Earth where laboratory analysis can provide definitive answers. That discovery shifts the entire search strategy. If Mars preserved biosignatures for nearly 4 billion years in surface rocks exposed to radiation and temperature extremes, imagine what might exist underground where conditions are far more stable. The subsurface becomes not just another place to look, but potentially the only place where definitive evidence still exists. Understanding what lies beneath Mars requires looking at ice. Not the dramatic polar caps visible from orbit, but buried deposits scattered across the mid-latitudes, hidden beneath dust and soil. The Mars Odyssey spacecraft, operating since 2001, mapped these deposits using neutron spectroscopy. The technique detects hydrogen atoms, which indicate water ice even when buried several meters deep. What emerged from that data was surprising. Ice exists far more widely than models predicted, in regions where current surface temperatures should make it unstable. The ice isn't recent. It's ancient, deposited during different climate periods when Mars's axial tilt was different and ice could accumulate at lower latitudes. As the climate shifted, dust covered the ice, insulating it from sublimation. Those deposits now sit frozen in time, potentially preserving anything trapped within them when they formed. The Mars Subsurface Water Ice Mapping Project combined data from multiple instruments to create detailed maps showing where ice likely exists at different depths. The maps identify specific regions, Deuteronolis mensae and Arcadia Planitia, where ice sits close enough to the surface that future missions could access it with existing drilling technology. But these aren't just resource maps for future astronauts. They're treasure maps for astrobiology. Here's why frozen ice matters for finding life. On Earth, microorganisms can survive frozen in ice for extraordinary periods. Bacteria extracted from Antarctic ice cores hundreds of thousands of years old have been successfully revived. The ice doesn't just preserve dead cells. It maintains dormant organisms in a state of suspended animation. If Mars ever had microbial life, and if that life existed when ice was forming, some of those organisms could still be locked in subsurface ice deposits, frozen but potentially viable. Even if they're not alive, the ice would preserve their cellular structures and organic molecules far better than any other environment on Mars. The Phoenix lander demonstrated this possibility in 2008 when it dug trenches in the Martian Arctic and photographed subsurface ice. The mission proved that accessing buried ice is technically feasible. What it didn't have was the analytical capability to search for biosignatures within that ice. Future missions designed specifically for that purpose could extract ice samples and analyze them for organic compounds, cellular structures, or even preserved DNA. But ice isn't the only subsurface environment worth investigating. Beneath Mars's volcanic plains lie networks of lava tubes, vast underground chambers formed when flowing lava drained away, leaving hollow tunnels. On Earth, lava tubes in places like Lanzarote in Spain's Canary Islands host thriving microbial communities. Bacteria colonize the tube walls, extracting energy from minerals in the rock. The tubes provide stable temperatures, protection from radiation, and in some cases, moisture from condensation. Mars has similar structures. Orbital imagery shows collapsed sections of lava tubes, revealing openings that descend into darkness. The tubes themselves could extend for kilometers underground, creating vast protected spaces where conditions differ dramatically from the harsh surface. Temperature variations would be minimal. Radiation levels would drop to nearly zero. If any water vapor exists in Mars's thin atmosphere, it could condense inside these tubes, creating localized humid environments. Research teams studying terrestrial lava tubes have found calcium and sodium sulfates, minerals that form through water-rock interactions and can preserve biosignatures. Those same minerals likely exist in Martian lava tubes. If microbes ever colonized these underground chambers, their chemical signatures could still be present, protected from the destructive forces that erase evidence on the surface. The energy problem presents a fundamental challenge for subsurface life. On Earth's surface, photosynthesis drives most ecosystems. Underground, that option disappears. Deep subsurface life on Earth survives through chemosynthesis, extracting energy from chemical reactions between rocks and water. Iron oxidation, sulfur reduction, methane production. These processes don't require sunlight, just the right chemical ingredients and liquid water. Mars's subsurface likely contains those ingredients. Volcanic rocks rich in iron and sulfur compounds. Groundwater, possibly in the form of brines that remain liquid at temperatures well below zero. But there's another energy source that could power Martian subsurface life, one that doesn't exist on Earth to the same degree. Cosmic rays. These high-energy particles from deep space constantly bombard Mars. On the surface, they're destructive, breaking apart organic molecules. Underground, they could be life-giving. When cosmic rays penetrate into subsurface ice or water, they trigger radiolysis, splitting water molecules into hydrogen and oxygen. That process releases energy-carrying electrons that microbes could theoretically harvest. Research published recently demonstrates that radiolysis could provide enough energy to sustain microbial communities in completely dark environments, deep underground where no other energy source penetrates. This fundamentally expands where life could exist on Mars. Not just in sunlit surface environments that existed billions of years ago, but in permanent darkness underground, sustained by radiation from space. That possibility changes what instruments future missions need. If cosmic ray-powered life exists in Martian ice or groundwater, it would produce specific chemical signatures. Elevated hydrogen levels from radiolysis. Organic compounds produced through chemosynthetic metabolism. Mineral alterations showing electron transfer reactions. Ground-penetrating radar can detect some of these signatures indirectly by identifying changes in subsurface ice structure or unusual reflective properties that might indicate biological activity. Both Perseverance and Zhurong carry sophisticated radar instruments specifically designed to probe beneath the surface. Perseverance's RIMFAX operates at frequencies that penetrate tens of meters, imaging subsurface structures with remarkable detail. Zhurong's radar revealed something unexpected in Utopia Planitia. Subsurface layers dipping at consistent angles, structures that match coastal deposits on Earth. The discovery provides strong evidence that an ancient ocean once existed in that region, with waves depositing sediments in patterns still visible underground billions of years later. Those ancient coastal environments would have been ideal for life, zones where water met land, where nutrients concentrated, where energy from sunlight and chemical reactions were both available. If Mars had a stable ocean for any significant period, life could have emerged there just as it did in Earth's oceans. The methane mystery adds another layer to subsurface speculation. Curiosity detected methane in Mars's atmosphere, but the concentrations vary dramatically and unpredictably. Sometimes readings spike to 7 parts per billion, then drop back to undetectable levels. That pattern suggests localized sources releasing methane in pulses rather than constant background production. On Earth, methane comes from 2 main sources. Geological processes like serpentinization, where water reacts with iron-rich rocks. And biological processes, methanogenic bacteria producing methane as a metabolic waste product. Both processes could occur on Mars. The question is which one, or whether both contribute. Recent analysis threw cold water on the biological interpretation. Researchers discovered that Curiosity's instrument chambers were contaminated with terrestrial methane before launch, and that contamination persisted despite attempts to purge it. The detected methane might not be Martian at all. But that doesn't close the book. Other instruments, including orbiters and Earth-based telescopes, have also detected Martian methane. If the detections are real, the short lifetime of methane in Mars's atmosphere means something must be actively producing it. Underground reservoirs slowly releasing trapped ancient methane. Ongoing geological reactions. Or possibly, hopefully, subsurface microbial communities. Finding the source requires drilling. Surface measurements can detect the gas but can't pinpoint where it originates. Only subsurface sampling can distinguish between geological and biological sources by analyzing the methane's isotopic composition and the geological context where it's found. Ancient sand dunes in Gale crater tell a story about how long water persisted underground. The dunes formed on Mars's surface billions of years ago, then were buried and lithified into solid rock. But before they hardened completely, groundwater seeped through them, depositing minerals in the spaces between sand grains. Analysis of those minerals shows they formed from water with specific chemical properties, slightly acidic, carrying dissolved minerals from surrounding rocks. The critical detail is timing. The dunes were already buried when the water arrived. surface water had long since disappeared. Yet underground, water continued flowing through porous rock layers, following ancient aquifer systems that remained active for millions of years after the surface dried. Those subsurface water systems could have been the last refuges for Martian life, protected environments where microbes persisted long after surface conditions became uninhabitable. Finding similar environments elsewhere on Mars becomes a priority. Ancient dune fields exist in multiple locations. If groundwater modified all of them, the subsurface hydrological system was far more extensive than currently understood. That search led directly to the Mars Subsurface Water Ice Mapping Project, SWIM for short. The initiative began with a straightforward goal: map every location on Mars where ice exists within a few meters of the surface. Not just general regions, but specific coordinates where future missions could land and drill with confidence. SWIM combined data from multiple spacecraft. Neutron spectrometers that detect hydrogen atoms, thermal sensors that track temperature variations, radar systems that penetrate underground, and high-resolution cameras that spot terrain features indicating buried ice. Each instrument provided one piece of the puzzle. Together they created detailed maps showing ice probability at different depths. 0 to 1 meter. 1 to 5 meters. Deeper than 5 meters. The project focused on mid-latitudes between 30 and 60 degrees north and south. These zones represent a sweet spot. Cold enough that ice remains stable underground, but not so cold that the surface becomes completely inaccessible. The maps identified two particularly promising regions: Deuteronolis mensi and Arcadia Planitia. Both show extensive ice deposits starting just centimeters below the surface. Future missions targeting those areas could access water ice with minimal drilling, making them ideal locations for both scientific investigation and eventual human bases. But mapping ice tells only part of the story. You also need to understand what that ice contains. Pure water ice, or ice mixed with salts and minerals that dramatically alter its properties? Phoenix answered that question in 2008 when it landed in Mars's far north. The lander dug trenches in the soil using a robotic arm, exposing bright white material beneath the rusty surface. Over several days, that material sublimated, turning directly from solid to gas. Definitive proof of water ice. But Phoenix discovered something else. Perchlorates. Salts composed of chlorine and oxygen that drastically lower water's freezing point. On Earth, pure water freezes at 0 Celsius. Mix in enough perchlorate and that freezing point drops to -70 Celsius or lower. That chemistry matters because it means liquid water could exist on Mars under conditions where pure water would freeze solid. Thin films of briny liquid might persist in soil pores, moving slowly through underground layers even when temperatures hover far below freezing. Those brines present both opportunity and challenge. Opportunity because liquid water, however salty, provides environments where chemistry can occur. Challenge because high salt concentrations create extreme osmotic stress that would kill most Earth organisms instantly. Any Martian microbes adapted to those conditions would need biochemistry fundamentally different from terrestrial life. Studies in Earth's Atacama Desert revealed just how specialized life becomes in such environments. The Atacama represents one of Earth's best Mars analogs. Extremely dry, high UV radiation, soils rich in perchlorates. Yet microbial communities persist there, clustered in specific microhabitats where moisture occasionally appears. Researchers deployed an autonomous rover in the Atacama, drilling cores to depths of 80 centimeters across a 50-kilometer transect. The rover operated under constraints similar to Mars missions. Limited power, no real-time human control, autonomous sample selection. It successfully retrieved 32 subsurface samples while validation teams manually collected 60 more samples at the same locations. Analysis revealed bacterial communities stratified by depth. Near-surface sediments hosted different species than deeper layers. Moisture content determined community structure. Geochemical analysis showed that soluble salts and specific minerals influenced water availability, particularly in deeper sediments where salt concentrations peaked. Crucially, colonization was patchy. Some samples contained thriving communities. Adjacent samples showed no detectable life despite similar chemistry. That patchiness suggests life at the edge of habitability exists in isolated pockets, not as continuous populations. The pattern has direct implications for Mars. If Martian life exists, it probably occupies scattered refuges rather than spreading uniformly through underground layers. Finding those isolated communities requires sampling many locations. One drill hole might miss life completely while another a few meters away strikes pay dirt. The Atacama work also demonstrated that rover-mounted drills can function reliably under Mars-like conditions. The autonomous system completed its sampling mission despite dust storms, temperature swings, and communication delays. Future Mars rovers equipped with similar drills could probe subsurface environments directly rather than relying solely on remote sensing. But drills reach only so deep. Phoenix dug trenches 10 centimeters down. The Atacama rover drilled 80 centimeters. Curiosity and Perseverance carry drills reaching perhaps 20 centimeters into rock. To access truly deep subsurface environments where conditions remain stable over geological timescales requires different technology entirely. That's where ground-penetrating radar becomes essential. Both Perseverance and Zhurong carry radar instruments designed to image underground structures without physical excavation. RIMFAX on Perseverance operates at frequencies between 150 and 1200 MHz, achieving vertical resolution of roughly 10 centimeters and penetration depths of 10 meters or more depending on soil properties. Roper on Zhurong uses two different frequency ranges. Low frequency for deep penetration, 15 to 95 MHz. High frequency for detailed resolution, 450 to 2150 MHz. The combination allows imaging of both deep structures and shallow features with fine detail. These radar systems work by sending electromagnetic pulses into the ground and measuring reflected signals. Different materials reflect radar differently. Ice produces distinct signatures. Rock layers appear as continuous reflectors. Buried craters or lava tubes create characteristic patterns. Salt-rich brines generate extremely strong reflections due to high electrical conductivity. Data from both rovers revealed subsurface complexity that surface observations completely missed. Perseverance's traverse through Jezero crater showed ancient river delta deposits extending meters underground, layered sediments recording multiple episodes of water flow separated by dry intervals. Zhurong's radar at Utopia Planitia detected those dipping coastal structures, but also something else. Anomalous bright reflections at depths of 10 to 30 meters. The signals match what you'd expect from either concentrated ice deposits or possibly liquid brines. Distinguishing between the two requires additional data, but either interpretation suggests significant subsurface water in that region. Meanwhile, lava tubes emerged as another priority target. Spacecraft orbiting Mars have photographed dozens of cave-like openings, dark spots on crater walls or volcanic slopes where surface material appears to have collapsed into underground voids. Analysis of those openings suggests they connect to much larger tunnel systems carved by ancient lava flows. On Earth, lava tubes form when the surface of a flowing lava stream solidifies while molten rock continues moving underneath. When the eruption ends and the lava drains, hollow tubes remain. Some terrestrial lava tubes stretch for kilometers and reach widths of 30 meters. Large enough to shelter entire buildings. Martian lava tubes could be even bigger due to lower gravity, allowing wider stable spans before structural collapse. Those tubes offer remarkable advantages as potential habitats. Protection from radiation. Surface radiation on Mars includes cosmic rays and solar particles that would deliver lethal doses to unprotected organisms over time. Just a few meters of rock provides complete shielding. Protection from temperature extremes. Martian surface temperatures swing wildly between day and night, summer and winter. Underground environments maintain relatively stable temperatures year-round. Protection from oxidizing surface chemistry. Martian soil contains perchlorates and other oxidants that break down organic molecules. Tube interiors remain isolated from surface chemistry. And crucially, protection from UV radiation that destroys organic compounds. Studies in Earth's lava tubes found thriving microbial communities on tunnel walls, feeding on minerals and moisture seeping through cracks. Those communities deposit distinctive mineral formations. Calcium sulfates, sodium sulfates, manganese and iron oxides. Precisely the types of biosignatures scientists hope to find on Mars. The stable conditions inside tubes could preserve such biosignatures for billions of years, protecting them from erosion and chemical degradation that destroys surface evidence. But there's an even more intriguing possibility. Active life might still inhabit Martian lava tubes. If water seeps into tubes from surrounding rock layers, and if chemical energy sources exist in that water, microbial ecosystems could persist in complete isolation from the surface world. Recent research added another potential energy source that doesn't require sunlight or volcanic heat. Cosmic rays. High-energy particles from deep space constantly bombard Mars. On the surface, they're mostly destructive, breaking apart organic molecules and damaging DNA. But underground, they might power life. When cosmic rays penetrate water or ice, they trigger radiolysis. The radiation breaks water molecules into hydrogen and oxygen radicals. Those radicals react with dissolved minerals, creating chemical species that carry energy. Hydrogen peroxide, molecular hydrogen, sulfates. Organisms capable of metabolizing those compounds could extract energy without any input from the sun. Earth hosts such organisms. Deep underground in South African gold mines, bacteria live in complete darkness 3 kilometers below the surface. They metabolize hydrogen produced by radiolysis of water interacting with radioactive uranium in surrounding rocks. The microbes have been isolated from surface ecosystems for millions of years, sustained entirely by radiation-driven chemistry. If similar processes occur in Martian ice deposits or aquifers, they could support chemosynthetic ecosystems regardless of surface conditions. The energy flux from cosmic rays on Mars is sufficient to produce substantial amounts of hydrogen and other reactive species. Calculations suggest radiolysis could generate enough chemical energy to support sparse but viable microbial populations in ice-rich layers or subsurface water. That mechanism works anywhere water and cosmic rays intersect. Polar ice caps. Mid-latitude ice deposits. Deep aquifers. Even ice within lava tubes. It expands the potential habitable zone on Mars far beyond locations receiving sunlight or geothermal heating. The implications stretch beyond Mars. Europa, Jupiter's ice-covered moon, harbors a subsurface ocean beneath kilometers of ice. Enceladus, Saturn's moon, shoots geysers of water into space from subsurface reservoirs. Both receive intense cosmic ray bombardment. Both could theoretically host radiolysis-powered ecosystems in complete darkness beneath their frozen shells. Back on Mars, the search shifts from abstract possibility to concrete targets. Where exactly should we look? The answer depends on what we're searching for. Preserved biosignatures from ancient life, or active ecosystems that might exist today. For ancient biosignatures, certain locations stand out. Gale Crater, where Curiosity has been exploring since 2012, contains layered sedimentary rocks deposited in an ancient lake environment. Analysis revealed something unexpected. Even after the lake dried up billions of years ago, groundwater continued flowing beneath the surface, seeping through sand dunes and depositing minerals in rock fractures. Those minerals include clays and sulfates that form only in the presence of water. More importantly, they can trap and preserve organic molecules for billions of years. Curiosity detected complex organic compounds in those rocks. Long-chain hydrocarbons containing up to 12 carbon atoms. On Earth, such molecules typically come from biological sources. Fragments of fatty acids that form cell membranes. But geological processes can also create them. The discovery doesn't prove life existed in Gale Crater. It proves the chemistry was right for life and that biosignatures, if they formed, could still be preserved. Then there's Zhurong Crater, where Perseverance is currently exploring. This crater once held a lake fed by rivers that carved channels through the rim. The rover recently examined a rock called Chiava Falls, collecting a sample named Sapphire Canyon. Analysis found something remarkable. Tiny mineral structures with cores enriched in gragite surrounded by rims rich in vivianite. That bullseye pattern matches chemical signatures seen in Earth sediments where microbes mediate electron transfer reactions. The pattern suggests, but doesn't prove, that metabolism occurred in ancient Martian mud. The sample awaits return to Earth for detailed analysis that rover instruments can't perform. If Mars sample return succeeds, laboratories will examine it atom by atom, searching for definitive proof. But what about living organisms that might exist now? The surface is lethal. Radiation, oxidizing chemistry, extreme dryness. Any active life must be underground. The question becomes, how deep? Surprisingly, not very deep in some locations. Computer models show that sunlight can penetrate up to 3 meters through dusty water ice. That's enough for photosynthetic microbes to potentially survive in shallow ice deposits at mid-latitudes. Those regions show extensive buried ice mapped by multiple spacecraft. The Mars Subsurface Water Ice Mapping Project identified Arcadia Planitia and Deuteronolis mensae as particularly promising sites. Radar data reveals ice layers between 1 and 5 meters below the surface, sometimes even shallower. Accessing that ice presents technical challenges. The Phoenix lander in 2008 successfully dug trenches and photographed ice in Mars' Arctic region. Future missions need similar or better digging capability. Drills that can penetrate several meters. Scoops that can excavate frozen soil. Systems that can operate in extreme cold without human supervision. Several space agencies are developing such technologies. Autonomous drilling systems tested in Earth's harshest deserts. The Atacama, where conditions approach Martian extremes. Rovers equipped with drills have successfully retrieved samples from depths of 800 millimeters, demonstrating that the technology works even in highly challenging terrain. But if active life exists deeper, beyond the reach of drills, how do we detect it? Indirect evidence might provide clues. Methane detections offer one intriguing possibility. In 2018, Curiosity measured seasonal variations in atmospheric methane levels. Background concentrations fluctuate, and occasional spikes reach 7 parts per billion. That's tiny, but significant. Methane survives only briefly in Mars' atmosphere before UV radiation breaks it apart. Detectable levels require continuous replenishment from some source. Either geological processes or biological activity. On Earth, microorganisms called methanogens produce methane as a metabolic waste product. Similar organisms could theoretically survive in Martian subsurface environments, metabolizing hydrogen and carbon dioxide to produce methane that slowly seeps to the surface. However, recent research complicated the picture. Contamination in Curiosity's analysis chamber might explain some detections. Terrestrial air accidentally introduced before launch created methane contamination 1,000 times higher than actual Martian concentrations. Despite repeated attempts to evacuate the system, traces persist. The debate continues. Are we detecting real Martian methane from subsurface sources, or instrument artifacts? Future missions with different detection methods will help resolve the question. Another indirect signature involves mineral formations created by groundwater. Recent discoveries show intricate structures in Martian rocks where water circulated through fractures long after surface conditions became inhospitable. Those structures resemble formations in Earth's subsurface where microbial communities thrive on minerals and moisture seeping through cracks. Clay minerals, carbonates, sulfates. All indicators of past water activity. All potential homes for ancient or even modern microbial ecosystems if water still flows in isolated pockets. The Zhurong rover provided additional evidence of ancient subsurface water. Its ground-penetrating radar identified layered structures beneath Utopia Planitia that resemble ancient shoreline deposits. Sediments dipping at consistent angles between 6 and 20 degrees, extending 10 to 35 meters deep along a traverse over 1 kilometer long. The structures match coastal deposits on Earth where waves and currents sort sediments by size. This suggests Mars once had a substantial water cycle with precipitation, surface flow, and crucially, subsurface infiltration. Water soaking into the ground, creating aquifers, perhaps sustaining life in protected underground environments. Could such aquifers still exist? Possibly, as brines. Pure water freezes at 0 Celsius, impossible to maintain liquid in Mars' current climate. But salt water is different. Perchlorates, abundant in Martian soil, dramatically lower the freezing point. Concentrated perchlorate brines can remain liquid down to -70 Celsius. Transient briny flows might exist just centimeters below the surface in some locations. The permafrost layer sits only a few centimeters down. Below that, conditions could occasionally permit liquid brine. But there's controversy here too. Radar observations from Mars Express detected what appeared to be liquid water beneath the South Polar ice cap. Bright radar reflections at ultimiscopuli suggested a subsurface lake. Follow-up observations found 3 additional smaller lakes nearby. The interpretation was that hypersaline perchlorate brines remained liquid despite frigid temperatures. However, Sharad, another radar instrument, detected only faint signals in the same region. Some observations found no signal at all. The discrepancy raises questions. Is it really liquid water, or something else creating unusual radar reflections? Clays. Hydrated minerals. The debate illustrates how challenging it is to definitively identify subsurface water from orbit. Direct sampling remains the gold standard. But drilling deep enough poses enormous challenges. Reaching truly deep aquifers, if they exist kilometers down, requires technology far beyond current capabilities. Heavy drilling equipment. Power systems to run it. Autonomous operation over extended periods. Contamination prevention to avoid introducing Earth microbes. Each requirement multiplies complexity and cost. So exploration focuses on accessible targets. Shallow ice deposits. Lava tubes with potential cave entrances visible from orbit. Ancient lake beds where groundwater once flowed. Those locations offer the best balance between scientific value and technical feasibility. They're places where biosignatures could be preserved and where instruments we can realistically deploy might detect them. Understanding what to look for helps. Earth's extremophiles provide templates. Organisms adapted to conditions similar to Martian subsurface environments. Halocycrophiles thrive in cold, salty conditions. Some survive in Arctic brine pools. Others in Antarctic ice. These organisms demonstrate that life can adapt to extreme salinity, sub-zero temperatures, and limited water availability. Methanogenic archaea live deep underground on Earth, metabolizing hydrogen and carbon dioxide in complete darkness. They represent potential Martian analogs. Desiccation-tolerant microbes survive in the Atacama Desert's hyperarid core, extracting moisture directly from the atmosphere when necessary. Research teams studying these organisms create artificial Martian soils and brines to test whether Earth extremophiles could survive Martian conditions. Many can, at least temporarily. That doesn't prove Martian life exists, but it proves the environment isn't automatically sterile. The search strategy emerges from combining all these factors. Target locations where water once flowed or ice now exists. Use radar to map subsurface structures without drilling. Deploy rovers with sophisticated instruments to analyze rocks and soils. Sample materials that could preserve biosignatures. Look for chemical patterns consistent with metabolism. Detect gases that might indicate active subsurface ecosystems. And eventually, drill to access buried ice or soil layers beyond the reach of surface scoops. NASA's Mars exploration program has outlined priorities through 2044. Subsurface exploration tops the list. Developing technologies to access caves, lava tubes, and polar regions. Characterizing water sources for both scientific and practical reasons. Future human missions will need water for drinking, oxygen production, and rocket fuel. Finding accessible ice deposits serves dual purposes. And the search for life, whether ancient or active, remains central. Because answering that question transforms our understanding of biology's place in the universe. The evidence keeps accumulating. Ground-penetrating radar on both Perseverance and Zhurong rovers can image subsurface structures dozens of meters down. RIMFAX, aboard Perseverance, operates at frequencies designed to detect buried sand dunes, lava features, and ice deposits. Roper on Zhurong does something similar. Both provide real-time subsurface mapping as rovers traverse the terrain. This technology reveals layers invisible to cameras. Rock boundaries. Density changes. Potential ice zones. In 2023, Zhurong's radar identified what appeared to be ancient coastal deposits in Utopia, Planitia. Subsurface reflectors dipped consistently at 6 to 20 degrees, extending along a 1.3-kilometer traverse. The pattern matched terrestrial shorelines. A prograding coastline where sediment accumulated as an ancient sea receded. The structures were 10 to 35 meters thick. Uninterrupted. Not dissected by later fluvial channels. Their low permittivity matched coastal sediments on Earth. This wasn't indirect inference. It was direct structural evidence that water once stood there, depositing layer after layer of sediment in a predictable geological sequence. What does that mean for life? Ancient coastlines represent zones where water met land. Shallow seas. Tidal zones. Places where nutrients concentrated. On Earth, such environments teem with organisms. Coastal sediments preserve fossils remarkably well. If Mars once had similar conditions, those same sediments could preserve biosignatures from billions of years ago. The Zhurong findings suggest we're driving over buried answers. Literally rolling across ancient seafloors that haven't been exposed to the surface in eons. Protected. Sealed beneath dust and regolith. Waiting. Meanwhile, research into how long biosignatures can actually survive in ice has produced encouraging results. NASA studies show that microorganisms frozen in permafrost can remain viable for extraordinarily long periods. Not just thousands of years. Millions. The ice acts as a time capsule. Metabolic processes cease. DNA remains stable. Cellular structures stay intact. When conditions improve, some organisms can revive. Others leave chemical signatures that persist even after cells die. Organic molecules locked in ice don't degrade the way they would if exposed to radiation, oxidation, or temperature fluctuations. Mars has abundant near-surface ice. The Phoenix lander photographed it in 2008. White ice exposed beneath the spacecraft's thrusters. Sublimating in the thin atmosphere. That was the first direct visual confirmation. Since then, orbital mapping has identified vast ice sheets across the mid-latitudes. Some buried just centimeters beneath the surface. Others meters down. The Mars Subsurface Water Ice Mapping Project has created detailed maps showing ice consistency at different depths. 0 to 1 meter. 1 to 5 meters. Beyond 5 meters. These maps guide mission planning. They identify where future landers could access ice with minimal drilling. But here's what makes this particularly intriguing. Recent discoveries at Gale crater show that groundwater persisted long after surface lakes disappeared. Ancient sand dunes that were soaked by subsurface water billions of years ago. The water moved through tiny fractures, seeping from higher elevations. It interacted with the dune material, left behind minerals that form only in the presence of liquid water. Clay minerals, sulfates, carbonates. These minerals can trap and preserve organic molecules, essentially creating microscopic storage vaults. The dunes eventually hardened into rock. And those rocks now contain a chemical record of what was dissolved in the groundwater, including, potentially, fragments of biological material. The finding suggests Mars remained habitable far longer than surface conditions alone would indicate. Even as the atmosphere thinned and temperatures plummeted, subsurface water continued flowing, creating niches, refuges where microbial life could have persisted. That possibility shifts the search strategy. Instead of only examining surface rocks, missions should target subsurface access points. Lava tubes represent one promising option. These form when lava flows solidify on the outside while molten rock continues flowing inside. When the eruption ends, the lava drains, leaving hollow tunnels. Some on Earth are massive, large enough to drive trucks through. Mars has similar features. Orbital images show numerous pit craters that likely lead to subsurface tubes. These tunnels offer stable environments. No temperature swings. Shielding from radiation. Protection from surface chemistry. On Earth, lava tubes in places like Lanzarote host thriving bacterial colonies. Scientists find calcium sulfates and sodium sulfates inside. Chemical markers indicating long-term microbial activity. The same signatures could exist in Martian lava tubes. And if they do, finding them requires getting inside. Which means developing rovers that can descend into caves. Navigate in darkness. Sample walls and floors autonomously. Another energy source could make subsurface life possible even without sunlight or geothermal heat. Radiolysis. When cosmic rays penetrate ice or water, they split molecules, releasing energy-carrying electrons. Microorganisms can harness that energy. It's chemosynthesis powered by radiation instead of chemicals from hydrothermal vents. On Earth, radiolysis supports microbial ecosystems in deep ice cores and isolated underground aquifers. The same process could work on Mars. Or Europa. Or Enceladus. Anywhere ice exists beneath a protective layer. The discovery fundamentally expands where we should look for life. Not just warm spots. Not just sunny locations. Anywhere with buried water and incoming radiation. Which describes much of Mars's subsurface. The ice at mid-latitudes. The polar caps. Buried aquifers if they exist. Detecting such life requires sophisticated instruments. Autonomous rovers tested in the Atacama Desert demonstrate what's possible. These machines move from rock to rock without waiting for instructions from Earth. They analyze samples. Identify interesting targets. Complete missions 3 times faster than traditional rover operations. Speed matters because Mars missions have limited lifespans. Dust storms. Equipment degradation. Power constraints. A rover that can cover more ground finds more potential biosignatures. The Atacama tests also validated drilling capabilities. The LIDA project deployed a rover-mounted drill in hyperarid desert terrain. It collected samples from depths up to 80 centimeters. Accessed sediment layers never before studied. Found bacterial communities stratified by depth. Moisture content. Salinity. Each layer hosted different organisms adapted to specific conditions. The same could be true on Mars. Shallow subsurface zones might host different life than deeper layers. Or different chemical signatures reflecting varying water availability over time. Which brings us to the methane mystery. Curiosity detected seasonal variations in atmospheric methane. Background levels fluctuate. Occasional spikes reach 7 parts per billion. Methane has a short atmospheric lifetime on Mars. Ultraviolet radiation breaks it down. So detecting it at all suggests active release. Either from subsurface reservoirs or from ongoing processes. Biological sources remain possible. Methanogenic archaea produce methane as a metabolic byproduct. These organisms live deep underground on Earth, metabolizing hydrogen and carbon dioxide, thriving without sunlight. If similar organisms exist on Mars, their methane would seep upward through soil and rock, emerging at the surface in localized plumes. that matches the detection pattern. Variable, unpredictable, concentrated in specific regions. However, controversy surrounds these measurements. Recent analysis suggests Curiosity's instrument may be contaminated. Methane trapped in the optics chamber from before launch. If true, the detections might not reflect Martian methane at all. Just persistent contamination. The debate remains unresolved. Orbital instruments haven't consistently detected methane. Ground-based telescopes see it sometimes. Other times not. The inconsistency makes interpretation difficult. Regardless of methane's origin, the broader geochemistry looks promising. Mars has abundant minerals formed through water-rock interactions. Clays, sulfates, carbonates. These form when water dissolves minerals, alters their structure, and precipitates new compounds. The process requires time, stable conditions, liquid water flowing through fractures or pooling in basins. On Earth, such environments support microbial communities. Bacteria colonize rock surfaces, extract energy from iron oxidation, sulfur reduction, mineral dissolution. The chemical pathways are well understood, and they don't require oxygen, making them plausible on ancient or subsurface Mars. Groundwater circulating through fractured bedrock could have created extensive habitable zones. Networks of tiny channels filled with brine, protected from surface extremes, chemically active, energetically viable. The biggest challenge remains access. Drilling tens of kilometers isn't feasible with current technology. But we don't necessarily need to go that deep. The most accessible targets lie within meters of the surface. Shallow ice deposits, recent mineral formations, rocks altered by groundwater, sediments deposited in ancient lakes. These locations balance scientific value against technical difficulty. They're places where rovers can realistically sample, where drills can penetrate, where instruments can analyze in situ. Future missions will focus there, developing better drills, more sensitive detectors, autonomous systems that reduce reliance on Earth-based control. Each improvement expands what's possible. And eventually, sample return changes everything. Bringing Martian rocks to Earth allows analysis with instruments too large, too power-hungry, or too complex for Mars. Laboratory equipment can detect trace organic molecules, sequence potential genetic material, identify isotopic ratios indicating biological processes. The Perseverance rover is already collecting samples. Sealed tubes cached at Jezero crater. A future mission will retrieve them, launch them to Mars orbit, transfer them to a spacecraft bound for Earth. The timeline stretches into the 2030s. But when those samples arrive, we'll have pieces of Mars to study in unprecedented detail, including the Chiava Falls sample with its potential biosignatures, Vivianite rims around Gragite cores, a chemical pattern seen in Earth sediments where microbes transfer electrons during metabolism. It's not proof, but it's suggestive. And it's exactly the kind of evidence that requires laboratory confirmation. The search beneath Mars isn't just scientific curiosity. It's fundamental to understanding biology's place in the cosmos. If life emerged independently on two planets in the same solar system, it suggests life isn't rare. That the universe might be filled with organisms wherever conditions permit. Alternatively, if we find nothing, that's equally informative. It means Earth's biosphere represents something uncommon. That the transition from chemistry to biology requires specific circumstances we haven't fully identified. Either answer reshapes how we view ourselves, our planet, our future. Because if Mars once lived and now doesn't, we're looking at a cautionary tale written in stone and ice. The pieces are falling into place, but the complete picture remains just beyond our grasp. Mars conceals its secrets beneath layers of dust, ice, and rock that we're only beginning to penetrate. Each discovery raises new questions while answering old ones. Ancient shorelines buried under Utopia Planitia. Groundwater-soaked dunes at Gale crater. Potential biosignatures in rocks collected by Perseverance. These aren't random data points. They're breadcrumbs leading toward an answer humanity has sought since we first looked up at that red dot in the night sky. The subsurface represents our best hope. Not because surface exploration has failed, but because Mars's surface tells a story of loss. Water vanished. Atmosphere thinned. Protective magnetic fields collapsed. Whatever life might have emerged there faced extinction-level changes. But underground, conditions remained more stable. Shielded from radiation. Insulated from temperature extremes. Protected from the oxidizing chemistry that makes the surface toxic. If Martian life survived anywhere, it survived there. Technology is catching up to ambition. Ground-penetrating radar images structures we couldn't see a decade ago. Autonomous rovers operate with minimal human oversight, making decisions in real time. Drills penetrate deeper. Instruments detect fainter chemical signals. Each improvement pushes the boundary of what's accessible. The caves we can only photograph from orbit will eventually host robotic explorers. The ice deposits mapped from space will yield samples. The deep aquifers that remain theoretical might someday be confirmed through seismic studies or improved radar. But we're not there yet. Current missions scratch the surface, literally. Phoenix dug centimeters. Curiosity's drill reaches maybe 20 centimeters into rock. Perseverance goes slightly deeper. These are reconnaissance missions. They identify targets. Prove concepts. Demonstrate that subsurface exploration is possible. The real work, drilling meters or tens of meters down, requires next-generation technology that's still being developed. Heavier equipment. More power. Better autonomy. Contamination protocols to ensure we don't mistake Earth microbes for Martian life. The timeline stretches ahead. Sample return in the 2030s. Human mission sometime after that. Permanent bases requiring water extraction from subsurface ice. Each step builds on previous ones. But the search for life doesn't wait for perfect technology. It proceeds with what we have, knowing that negative results are still results. Finding nothing in accessible locations doesn't mean life never existed. It means we need to look deeper, in different places, with better tools. Earth's extremophiles prove that life adapts to conditions we once thought impossible. Bacteria thriving in Antarctic ice. Archaea metabolizing chemicals in pitch-black caves 3 kilometers underground. Microbes surviving years of desiccation in the Atacama, then reviving when moisture appears. These organisms demonstrate that the requirements for life are more flexible than textbooks suggested. Mars's subsurface might not be comfortable by our standards, but comfort isn't necessary. Just liquid water, chemical energy, and protection from the most destructive environmental factors. The cosmic ray hypothesis adds another layer. Life powered by radiation instead of sunlight or geothermal heat. It sounds like science fiction, but the physics works. The chemistry checks out. Earth hosts proof-of-concept organisms in deep mines and ice cores. Mars receives constant cosmic ray bombardment. That radiation penetrates ice and rock, triggering radiolysis that produces chemical energy. If Martian microbes evolved to harvest that energy, they could persist indefinitely in buried ice deposits, completely independent of surface conditions. No need for volcanic activity. No need for recent water. Just ancient ice and incoming radiation. Proving it requires sampling. Not radar images or spectroscopic analysis from orbit. Actual physical samples brought to instruments capable of detecting the subtle chemical signatures metabolism leaves behind. Isotope ratios that indicate biological fractionation. Organic molecules too complex to form abiotically. Cellular structures preserved in minerals. DNA, if we're extraordinarily fortunate. These signatures exist in Earth's oldest rocks despite billions of years of geological activity. Mars, with its geologically dead surface, might preserve them even better. The methane controversy illustrates how challenging this search becomes. Detections from multiple instruments across decades. Seasonal variations suggesting active sources. Then questions about contamination. Debates over whether the methane is even Martian. Science doesn't provide instant answers. It accumulates evidence, tests hypotheses, refines understanding. Sometimes that process takes years or decades. The methane question will resolve when we can sample subsurface reservoirs directly, analyzing isotopes that distinguish between geological and biological sources. Meanwhile, missions continue. Perseverance collects samples at Jezero crater. Zhurong maps subsurface structures at Utopia Planitia until dust storms force it into hibernation. Mars Reconnaissance Orbiter photographs potential cave entrances. Mars Express radar probes beneath polar ice. Each dataset adds detail to our understanding of what lies beneath. Where ice concentrates. Where ancient water flowed. Where minerals formed under conditions compatible with life. The map of Mars's subsurface grows more detailed with every orbit, every radar pass, every drill hole. Future missions will target the most promising locations identified through this reconnaissance. Landers equipped with deep drills. Rovers capable of descending into caves. Instruments sensitive enough to detect biosignatures in parts per trillion. Sample return missions that bring Martian material to Earth's best laboratories. Human explorers who can make real-time decisions, adapting to discoveries as they happen. Each mission generation builds on lessons learned from predecessors. But the fundamental question remains unanswered. Does life exist beneath Mars, or did it ever? We have suggestive evidence. Compelling chemical signatures. Geological contexts that match habitable environments on Earth. What we don't have is definitive proof. A fossil. Preserved cells. Unambiguous biosignatures. The kind of evidence that removes all doubt. That evidence might be waiting in subsurface ice at Arcadia Planitia. Or in ancient coastal sediments beneath Utopia Planitia. or deep in lava tubes we haven't explored yet, or kilometers down in aquifers our current technology can't access. The search continues because the question matters. Not just scientifically, but philosophically. If Mars developed life independently from Earth, biology isn't unique to our planet. It's a natural outcome when conditions align. Chemistry becoming biochemistry. Molecules organizing into self-replicating systems. Evolution beginning its patient work. That would mean the universe likely hosts life wherever liquid water, energy sources, and chemical building blocks coincide. We're not alone, even if we're separated by vast distances. Alternatively, if Mars remains sterile despite having all the ingredients, that's equally profound. It suggests life requires something beyond liquid water and chemistry. Some spark, some transition we don't fully understand. That would make Earth's biosphere precious in ways we're only beginning to appreciate. A rare phenomenon in a mostly lifeless cosmos. Either answer changes how we see ourselves, our world, our responsibilities. Mars holds that answer beneath its surface, encoded in ice and rock and ancient sediments. We're developing the tools to read it, the drills to access it, the instruments to interpret it. What we find there, or don't find, will reshape our understanding of life's place in the universe. The rust-colored surface conceals depths we're only beginning to explore. Each meter down reveals environments more stable, more protected, more likely to preserve what surface conditions destroyed. The search has just begun. And beneath the dust, beneath the ice, beneath the ancient lava flows, Mars waits to tell us whether we've been alone all along, or whether life found a way on two worlds in the same solar system. The answer is there. We just need to dig deep enough to find it.